Okay, YouTube, in this video we're going to be exploring what we call a normal distribution. And up until this point, we've been looking at data sets and discussing, averages, mean, median, and mode, and also illustrating them using, I guess, what we call histograms or a bar graph. And so these bar graphs often, we see that, if we were to look at like weight, or we could say even like height, or we could look at another variable like temperature. These things, we would get some type of distribution of things here. And I would say that a lot of things in nature, what you'll find a lot of the time is that the average height or the average weight or the average temperature is some moderate thing, and we would consider it to be, what we call normal. The average is normal. And things that are far away from the average or further away from the average would necessarily become less common because it's not the typical thing, and that's what average stands for. So when we look at histograms that are shaped like this, where in the middle here we have some like average height, average weight, average temperature, and as we get to the extremes, as we move away from this, we'd say that these events are less common to occur on their own on the outside because very high temperatures, very low temperatures are not close to the average. So when we look at distributions in which data is packed around the average, and as we move away from the average weight, height, temperature, whatever variable type we're looking at here, it drops off. We get this bell-shaped curve, and it kind of gives us this idea that many things, many variable types in nature would occur this way. And so if we were to look, for example, at a random sample of 100 women, perhaps we look at their weight here. What we would see is that the average would be somewhere close to the middle here, and we could see how this pans out. Now, would this be perfectly bell-shaped or normally distributed here? You can see that the left side's a little heavier than the right side. That I don't mean like heavy in terms of weight, but I mean in terms of there's more data on the left here than there is on the right. But overall, you can see this pattern here makes this bell-like curve. Basically, what we want to do is use this idea that if we were to be able to collect more women in the sample, more than just 100, we would have more data. And if we were to take the size of these classes and maybe split them in half so that we have more classes here, what you're going to see is the more classes you have and the more data you have, the better picture you have of the overall weight of, say, the class of women in general. So we could say that increased sample size and class width decreased, we get this better picture here. Even again, if we get more people in our sample, the more people we get, the closer we are to describing the entire population of people. And the class width is decreasing. Eventually, if you were to capture every single woman and decrease your class width to near zero, you would see this subsection of cross sections here that would make up this entire bell-shaped curve that we refer to as a normal distribution for a population. So to describe a normal distribution, to describe a normal distribution here, if we wanted to look at what its characteristics are, we would say it's shaped like a bell. Okay. The average, as a matter of fact, the average value is the same as the median and mode, and is directly in the middle of the bell. And so we can see that as we move away from this average spot right here, and we should really label this here, this is the average. And you notice that I said with the normal distribution, if it's perfectly symmetrical like this, then we would say that this is the same as the median also, and the same as the mode here. All three of those would be equal. Another thing that we want to say about the normal distribution is that it is symmetrical about the mean. And so remember, what we mean by symmetry is that we could cut it about this line of symmetry and it would fold over onto itself. So symmetrical about the mean, or what we refer to as the average. Okay, and so basically here's what we're going to be doing is describing data sets that are normal, let's say for a group of 100 women, and having their data. What we could do is assume that if this 100 women really is a good subset of the entire population, then perhaps we could model what the entire population would look like based upon just our sample of data here. So here's what we're going to do. Just like we would use maybe a circle to model like a tire, what we're going to do is we're going to use the perfect normal distribution curve here, the perfect bell, to model what the population of women would look like if we knew this data right here. And we could measure things such as weight, height, heart rate, blood pressure, sodium levels, etc. These things tend to be normal. So let's take a look at our normal curve here and go further into what we know about this perfectly normal curve that we use as a model for normally distributed data. So we say that a normal distribution with a mean of mu, okay, so you would pronounce this as mu, or mu, I guess you would say here, but it is this Greek letter that looks like a U here. If you ask me, it looks like a U that has a longer tail on the front. I've even had people say that it looks like the letter M with a very long tail on the left side here. But we say the Greek letter mu, this represents the mean. And we say that the standard deviation, it's this little O that has a tail on the right side of it, is a Greek letter sigma here. And this sigma stands for the standard deviation. So one thing to be clear on is this: mu is the mean, and sigma is the standard deviation. Now, you'll notice that they use mu and sigma to represent mean and standard deviation, I hope, because they just start with the same letters in the Roman alphabet here, M and S. But when we look at the mean, we'd say this is the most typical case. Now, this term that you see down here, standard deviation, this is the average deviation or spread of our data from the mean. And so when we look at the standard normal distribution here, what I want everybody to notice is this. We would say that this normal distribution that would represent what our, I guess, population would look like if we had the data for everybody in our classes were small enough, what this does is it represents the entire population. And so we say that the total area under the related normal curve is 1. That is to say 100% of our data has to lie underneath this curve because this curve represents the entire population. Now when we look at these three figures here, 68%, 95%, and 99%, this is what we refer to as what we call the empirical rule. You don't need to know that it's called the empirical rule, but you may hear it called this. And what it basically does is it describes that if you had a population that is exactly normally distributed, then what we're going to see right here in the middle, okay, is the average. You notice that they wrote a mu here. So this is our average data value here, our average height, our average weight, our average temperature. And as we go to increased temperatures over here on the right or decreased temperatures over here on the left, you can see that this height of this curve is dropping because it's less likely to occur. So often what we're trying to do here is find the area under the curve that lies between a set of x values on the x-axis. And so what we're going to say is, in general, about 68% of the area always lies within one standard deviation of the mean. So when we say standard deviation, you're going to see this u, or mu, plus sigma here on the right and mu minus sigma on the left. What we've essentially done is taken the average spread and we went to the right sigma units, or one average spread above the mean and one average spread below the mean. So these two x values down here we say is the average plus one standard deviation, the average minus one standard deviation. You can see that what this is indicating is that between these two parts of our curve, here and here, the total area under the curve is 68% of the total population. So it is always fair to say, always, if it is a normally distributed population, that 68% of the people will lie within one average spread of the mean above and below it. Likewise, we could say, what if we were to go two average spreads above the mean? That is to say, the mean plus sigma. So to go one spread plus two spreads, say between here and two spreads to the left, two standard deviations to the left, we could say that between here and here, 95% of the data must lie. And we'd say if we were to go three standard deviations to the right and three standard deviations to the left, by the time we make it out to there, you can see that our diagram indicates that 99.7% of the population always lies within three standard deviations of the mean. So you'll notice that on both of these curves here, that we go three standard deviations to the left and three to the right. And the reason why is because if we were to go even a fourth standard deviation to the right, this would be mu plus 4 sigmas here. And if we were to go 4 standard deviations to the left, mu minus 4 sigmas, what you would see is that essentially we would have already almost 100% of our people when we were out 3 standard deviations. So with normally distributed things, we usually only go 3 standard deviations to the right of and left of the average, which is in the middle, and we call that the mean. Okay, so you could see that from our second statement here, about 68% of the area lies within one standard deviation of the mean. If we were to read that, what we could say is it must follow then that because our curve is symmetrical and that 100% of the population lies under the curve, then we could say that 50% of the population has to lie to the right of this curve, and the other 50% has to lie to the left of this curve. So that would be 100% of our data. But likewise, because of the symmetry, we could say because 68% of the data lies between these two standard deviation values here, one above and one below, then we could say that 34% of the data lies within one standard deviation above the mean, and 34% of the data must lie between the average and one standard deviation below the mean. And because of this symmetry, we could also deduce these other values out here. So what I'm going to say is that it's worth you knowing that this is 34% between 0 standard deviations above the mean and 1 standard deviation above the mean. In other words, between the average and one standard spread above the mean, 34% of the data must lie there. 13.5% is always between 1 and 2 standard deviations above, and we could say this is 2.35% between 2 and 3 standard deviations. And then everything above this is so small that it's only 0.15%, so we tend to neglect it. So the areas under this normal curve, what we want to do is basically interpret this as the entire population. And so we can interpret the areas under the curve as probabilities in a normal distribution. So in a normal distribution, we say that the probability that a randomly chosen x value is between two values, a and b, is given by the area under the normal curve between a and b. So to give you more of a solid example here, if we were to say that we have a normal distribution, let's go ahead and draw on our bell curve here. What we want to start with is just kind of say like we have an average here. And let's say the average weight of a bunch of, say, teenagers is 100 pounds. We could call this weight here. And we'll go with the standard deviation of 10. Okay, so we say 110, 120, 130. There's our 3 standard deviations above the mean. And if we were to go 3 standard deviations below the mean, going down by 10s, we'd say this is 90, this is 80, and this is 70. What we essentially want to be good at doing is saying, because we know the average is 100 and we know the standard deviation is 10, then the population probably looks like this based on the sample. So the real question is going to be, what's the probability that we grab somebody at random that's greater than 110 pounds? And you could see that really what we're going to be looking at is this 110 pounds right here. We're looking for the percentage of the population that lies over on this side of the curve. And you could see that from up here, it'd be really easy for us to just go up here and add up 13.5% plus 2.35% plus 0.15%. But that would really be representing the probability that we grab somebody that's greater than 110%, because what you're saying is that's the percentage of the population that's greater than 110 pounds here in this particular example. So here's what I want to do. I'm going to look at a couple of pure examples here of just calculating some probabilities using our empirical rule. And so for this first example, you can see that it's already kind of sketched out for us here. It says that a normal distribution has a mean of mu and a standard deviation of sigma. It says an x value is randomly selected from the distribution. Let's find the probability that x is greater than or equal to the mean minus 2 standard deviations, but at the same time is less than the mean. So we'd say that this is the mean right here, and this is 2 standard deviations left of the mean. So what you can see here is something that we would have done by hand but has already been done for us. We see our normal distribution here. And so in the middle, of course, we put our average here. And it looks like they've gone 3 standard deviations to the right and 3 to the left. When we try to find this probability right here, what we're really trying to do is find the area under the curve between the two indicated values here. And so what we see here is our 2 indicated values are on the left, the average minus 2 standard deviations, so that would be right here, between this x value and the mean here. If we were to grab some random x value on this interval, what would be the probability we grab it? And it's going to be equal to the area under the curve between those 2 x values there. So we would say that because we know that this is 34% right here, 34% between 0 and 1 standard deviation below the mean, and because we know this is 13.5% right here, then we would say that the total probability right now would be our 34%, okay, plus 13.5%. The probability that we randomly grab an x value between these 2 indicated values then would be, looks like 47.5% chance. So there's a 47.5% chance that we randomly grab somebody that's between these two indicated values. What we're going to look at here with this next example is essentially one that we're going to draw out on our own. So let's read this first. It says a normal distribution curve has a mean mu and a standard deviation of sigma. It says an x value is randomly selected from this distribution. Let's find the probability that x is less than mu plus 2 sigma. So let's go ahead and start with this. What we're going to do is we're going to draw out our normal distribution. And with respect to drawing this out, we always put the average right here in the middle. So we're going to label this mu. And then I'm not going to label these exclusively because it's just a lot of labeling. But what we can see is that I'm going 3 standard deviations to the right and 3 standard deviations to the left of our mean, as we usually do. So we're saying, what is the likelihood that we grab an x value down here on the x-axis that is less than the average plus 2 standard deviations? So I would say mu plus 2 sigma would be this mark right here. What I'm going to do is I'm going to switch over to like an orangish color here. And we're saying, how likely is it that we grab an x value that's to the left of this? So if I were to shade this in, we would say that really then it's the percentage of the population that lies to the left of this. And so what we're going to see here is that we've got a lot of different subsections to add up here. We have 13.5% that lies here. We have here 34%, okay, because of our empirical rule. Here we have another 34% of the population. Here we have the other 13.5% of the population here. And then we have down here, this is, remember, 2.35, okay? So we'd say roughly 2.35 in here, 2.35 here, and then out here we have roughly 0.15. So just coloring this in, what we're going to do is we'll just grab our calculator here and we'll add these values up. So we have 13.5, let me try that again, 13.5 plus 13.5 plus 34 plus 34 plus now the 2.35 plus the 0.15. What we get is 97.5% of the area here. So we'd say the probability that we randomly grab an x value that is less than 2 standard deviations above the mean is pretty good because most things lie in and around the average. So here's what I'd like for you to try is looking at these examples next with me here that do not involve kind of a pure example here but involve some numbers. Cheers.